Greetings and welcome, friends. Today we're talking about a very special type of logarithm, common logarithms. That's right, they're common in the sense that if they were a Magic the Gathering card, they would be of white rarity, or World of Warcraft. It wouldn't be purple as in like epic, rare loot sort of thing. It'd just be common, happens all the time. And it turns out that common logarithms are logarithms with base 10. And even better than that, lazy mathematicians decided, because they're so common, let's just never write 10 again. So if you have log of m, that is the same as writing log base 10 of m. They are one and the same, communicating the same thing, not unlike when perhaps you might remember, like having like a 2x. If I asked you what the exponent was here, you'd be like, oh, there's a little invisible 1. Right? Or if I had like this of this and I asked you what the index was, you'd be like, oh, there's a little invisible 2, right? In the world of logarithms, or actually let me phrase it this way, 10 is the hobbit in the land of logs. This is actually a quote on the Math 3 final exam from Jordan Labonte. Yeah, famous American mathematician. So, here we go. Let's do some work with these. Really, nothing too different so far. Let's do a little example. Oh, that's a terrible X. Yep, boxy box. So evaluate, and I've got 3 little examples here. What is log of 1,000, log of 1, and log of 1/100th? So log of 1,000, remember, is implying that the base is 10. And by the way, common logarithms is how your calculators communicate as well. So if I type in log 1,000, that's what the calculator believes I'm doing. 10 to the what is 1,000. So 10 to the what is 1,000? 3? 10 to the third power? Yeah. 10 to the third is 1,000, right? Here we go. Bam. All right, 10 to the what is 1? 1, that would 10 to the first is 10 though. Anybody? Because in fact anything to the 0th power is 1. Yep. And how about 10 to the what is the 1/100th? So 10 to what power is 1/100th? Well, it has to be negative in order to generate that fraction. And 10 to what power is 100? -2, right? So so there we go. Not too shabby. And the next series of problems, this is actually not unlike how original logarithmeticians, if that's a word, would have generated tables for logarithms in order to figure this out. Where once I have a few log facts, I can actually expand them using some properties of logarithms to getting other values. So suppose log 2 is 0.301. It's technically an approximation. And log 3 is 0.477, another approximation. Find log 4. So log 4, if I wanted to calculate that, and I didn't have a calculator, but I had these 2 previously known facts, well, I might be like, wait a minute, log 4, I could think of that as, that's the same as log of 2 squared, right? Right, because 2 squared is 4. And using my little exponents property of logarithms, the power property, I could move that 2 out front, so that's going to be the same as 2 times log of 2. And I know what log of 2 is. So therefore, this must just be 0.602, roughly. Right, so I can use properties of logarithms and previous facts to kind of build off of that to answer that question. Which, by the way, this means that 10 to this number should equal 4. 10 to the 0.602 equals 4. And in fact, it does, or would be close because that's an approximation. All right, how about using this question? Well, because this problem's got additional parts. Yep, good question. So what is the log of 6? 10 to what power is 6? Now question, is this going to be bigger than 1 or less than 1? Bigger, yep. Just to be clear, I'll repeat myself. Bigger than 1 or lesserer than 1? Why do you suspect that it's lesser?
Wait a second.
This is asking the question, 10 to what power is 6?
Probably more than that. Because log 3 times 2 is...
Well, 10 to the first power is 10. So 10 to what power is 6? This is less than 10, so this number must be less than 1. Okay, so just to point that out, you can kind of figure out some things like that. So I don't know log of 6. I know log of 2, I know log of 3, so how could I rewrite this to make it beneficial for us? Log of 2 times 3, that's different than log of 2 times log of 3. And the log of a product is the same as the sum of 2 logs. So it's the same as log of 2 plus log 3. And hey, I know those values. That's 0.301, of course, and 0.477. And so that's going to equal 0.778. And notice that is in fact less than 1, as I suspected earlier. Okay, all right, this is getting interesting. What about this? Using my previously known logarithms. So I know 2 and 3. So how could that help me find an 8th? So that's the same as log of what? Ooh, we're getting warmer. 2 cubed is 8. 1 over 2 cubed is that. Actually, 1 over 2 cubed would be interesting as well. I could technically do that with some properties. Maybe I'll look at that in a second. I'm going to write this as 2 to the negative cubed, because that is the same as 1 over 2 cubed. And then using my power property, we'll move this negative 3 out front. And I'll have negative 3 times log of 2, which is negative 3 times 0.301, of course. And I'll get negative, what is that, 0.903. Okay, all right, this is working. So you can see that with a handful of starting facts, I can actually branch off to other log facts, and then I could actually even use those log facts if I wanted to build new ones. And that's what eventually they did. They built tables of logarithms that then would be used as reference. Okay, so if I only know 2's and 3's, how could I find log of 18? Ooh, good call. Right, 2 times 9 is 18, so 2 times 3 squared. The log of a product is the sum of 2 logs, so that's log of 2 plus log of 3 squared. And I think I technically did some work with this. Did I do that one? No, I didn't. I did 2 squared earlier. That's fine. And then I could use the power property, so that's log of 2 plus 2 times log of 3. And that, of course, is the 0.301 plus 2 times 0.477. And you can see that without too much fuss, I can actually find this new logarithm. 2 times 0.477 is 0.954. And then add them, and I get 1.255. Which is what log of 18 is, which is also, that also would be telling me that 10 to the 1.255 should be about 18. Right, and notice that 18 is bigger than 10, so that's why the exponent had to be bigger than 1. And 18 is also less than 100, so that's why the exponent had to be less than 10 squared, being 100, which is, right, less than 2. So, okay, cool. This next example deserves maybe its own, I might even give this one its own example box. I think I'm gonna do it. And it's even a capital F this time. Find log 3000. So that's the same as log of 3 times what? 1,000. Now, we didn't know log of 1,000 off the get-go. However, the log of a product is equal to the sum of two logs, right? So that's log of 3 plus log of 1,000. Log of 3 is the 0.477 plus log of 1,000. 10 to what power is 1,000? Third power, because 10 cubed is 1,000. So this would equal 3.477. Cool. And it turns out there's a couple little vocab terms I want to point out here. I'll properly define them in a moment, but this part here, the 3, is referred to as a characteristic. I ran out of room. That's so sad. Oh my goodness. Oh, what will I do? There we go, characteristic. And the 0.477 is called the mantissa. Yeah. Crazy names for these things. The characteristic is always going to be a positive integer. And the mantissa will actually be 0 is less than m is less than 1. It's going to be the decimal part. So, let's write down those proper. Make it proper. The mantissa. Coming at you. And I might as well give you the characteristic as well. So the mantissa is the logarithm of a number between 1 and 10. Thus the mantissa is greater than 1 and less, greater than 0 and less than 1. And the characteristic, one way you could think about it is it's the exponent of 10 that is used to write the number in scientific notation. So for instance, when I said log of 1,000, I could have thought of that as log of 10 to the third, right? That's the scientific notation. And that could have been thought of 3 times log 10, Log 10 is just 1 because 10 to the first is 10. And the mantissa is the 3, and notice the agreement between the 3 and the 3 here. And that's what they're referring to here, like so. So, let you guys write that down. Internet friends, feel free to fast forward a little bit if you need to. Since you don't have to wait around for us, you can skip to the future. Craziness. So, there's like a car door glare there right now. It's sad. Can't see that online. So, mantissa characteristic. Oh, it was the other window. Oh well.
Wow, what is that?
Glare.
It's a glare from a vehicle over here. Oh well.
That is pretty awesome.
So, they just closed their door. That's awesome. So anyways, the internet didn't get that awesome live demonstration. So let's do this example. So find the log of 0.0007. And what we can do is, there's actually a couple ways to do this. Sometimes the scientific notation is almost easier. But I could think of this as being log of 7 times 0.0001 if you wanted. So the log of a product is the sum of two logs, so that's the same as log of 7 plus log of 0.0001, which I don't know if you guys recognize 0.0001 yet. I could also write that as, well, a couple different things. Actually, yeah, we'll do that in a second. I'll come back to log 7. We're going to end up either looking that up or getting that from a calculator in just a moment. But log of 0.0001 would be the same as log of 1 over 10,000, or I could view that as 10 to the negative 4th power, really. It's probably the easier way to 1 times 10 to the negative 4th power, if you want to think about it kind of like that. And log of 7 happens to be equal to 0.845.
That's in a calculator, right?
Yeah,
Okay.
yeah, you just hit log 7. Or it would be kind of like how I gave you the information earlier at the beginning of those other examples. So, this is 0.845. And what do you think this is equal to? Ten to what power is 10 to the negative 4th?
Negative 4.
Yeah, it's just negative 4. And if I combine these, I actually get negative 3.155. And this is where this is actually a little bit bizarre. I think I said earlier that the characteristic had to be positive, but it's actually, I was wrong. It's the mantissa. So the fact that this is a negative number, we actually wouldn't want to write it this way. I would just go to the next largest negative and then kind of find the positive mantissa version. But I'll show you this problem in scientific notation. It's a lot easier. So this is actually the characteristic, and this is the mantissa here. But if I had just done this problem originally, scientifically, let's just say I did it over here, using another technique, I could have written this as log of 7 times 10 to the negative fourth. And then that would have just been log of 7 plus log of 10 to the negative fourth, and then you would have gone from there. So the scientific notation can sometimes actually be easier, because sometimes if you end up with this, it's a little bit weird to work backwards to try to find the characteristic. But I think the scientific notation technique will work good every time. And then that also comes into the definition of characteristic. It's the exponent of 10 that is used to write the number in scientific notation. So the characteristic's a little bit more obvious that way. So let's talk about how do I find logarithms when it's in a base that I don't know. Like, because your calculator can work in base 10 very easily, but what happens if I want to find out, say, log base 2 of 3? If I want to figure out what is 2 to what power is 3, it turns out there's what's called the change of base formula. So it says if a, b, and n are positive numbers, and neither a nor b is 1, then the following equation is true. So this is the change of base formula. This is the way you could find things like log base 2 of 3 on a calculator. Actually, I think some of our graphing calculators do actually allow you to do bases for logarithms, but I find this much more interesting, nonetheless. So if I want to figure out what log base 2 of 3 is, what this is saying is I could rewrite the base as the of in the denominator, and I could write the of as the of in the numerator, where I have 2 logs of any base. So b could pretty much be anything. It's got to be positive and not 1, but so I could write this as log of 3 divided by log of 2. So if I plug this in a calculator, I could work in base 10, log base 10 of 3 and log base 10 of 2, and figure it out from there. Or technically, actually in this case, I happen to know those numbers from the beginning of this lesson, 0.477 and 0.301. And if I divide that out, I get 1.585. And it happens to work out. And what I want to point out is that the bases here could actually be anything. I could have had like log base 3 of 3 and log base 3 of 2. Or I could have had log base 100 of both of those. So the base for the change of base formula doesn't matter. It's whichever is most convenient for you. But the idea is that we merely take this and move it up top. We take this, and it's the inside of the log on the bottom. And now I can answer these questions. So 1.585, what does that mean? That means that 2 to this power is equal to 3. All right, that's what that actually is referring to, if you want to think of this answer exponentially, so to speak. And the last thing we get to talk about is anti-logarithms. And you might be like, this, or actually no, I lied. It's not the last thing. The last new concept we're talking about. Then we're going to do a couple little solving ones, but actually, nope. I lied. That's not even an example. Oh, terrible. We'll do an example in a second, though. Man, oh man. So, anti-logarithm. If log x equals a, then x equals the anti-log of a. Now, that doesn't necessarily seem very helpful. I think this little explanation I put down here makes more sense, because the anti-log is just like sine inverse, all right, was the inverse of sine. Cos inverse was the inverse of cos, right? Arc sine was also an inverse of sine function. It turns out the anti-logarithm is just the inverse of a logarithm. But notice this little note here I said the inverse of a logarithmic function is an exponential function. Because when we first learned about logarithms, I said that they were the inverse of exponential functions, so therefore the inverse relationship is mutual. It goes both ways there. So if now think about it this way. It's kind of like the enemy of my enemy is my friend sort of thing. The inverse of an inverse was the original function. So if I wanted to calculate what the anti-log of a number is, all I'm doing is calculating what 10 to the 8th power is. A as an A and not 8 as an 8th. 8th power. That's kind of a weird way to phrase it. So, as a quick example of that, if I wanted to calculate, say, and I hope I don't run out of room here. I might only do one more example after this. We'll see. If I wanted to calculate what anti-log of 3 is, that's the same as 10 to the 3rd power, which is 1,000. So it's just kind of like a fancy way to write it. I do think this notation has shown up on some sort of testing. I forget if it was SAT or kneecaps or something, but it has shown up. So it is important to know that sometimes mathematicians have multiple ways of writing things. And yeah, I think I'm actually going to skip down to my last example. For sake of room, that's fine, that's fine. Put some of our change of base stuff and properties all together. So what if I want to solve the equation 5 to the x minus 1 equals 2 to the x? So this is an exponential equation, all right, where I've got variables and exponents, and I want to know what values would be true for those. And this sort of question is good for answering things like, if I invest $1,000 at a certain interest rate, how many years would it take to reach $1 million, right? That is a variable and an exponent kind of question that logarithms would be able to help us answer. So to do this, the first thing I'm going to do is take the log of both sides. So I'm going to rewrite this as log of 5 to the x minus 1 equals log of 2 to the x. Because the only way to get a variable out of an exponent is with logarithms. That's one of the very powerful abilities that logarithms have, is that they can, right, using our little power property, I can just completely take exponents and make them coefficients, so to speak. So this I could think of as x minus 1 all times the log of 5 equals x times the log of 2. And now what I'm going to do is I'm going to distribute here first of all, and I'm going to bring all of my logs together that have x's. So let's distribute here. So I'll have an x log 5 minus log 5 times negative 1 would be negative log 5, or negative 1 log 5 if you want that, equals x log 2. And like I said, I've got logs all over the place, but I'm going to group the logs that have variables on one side and the logs that don't on the other. So I'm going to actually move this log 5 to the other side. And I'm going to bring this log over here because it has an x. So just think about log 2 and log 5 as just numbers. Imagine if this just said 5x minus 5 equals 2x. And I'm just bringing my x's together. And now these don't really combine as like terms as nicely as you'd hope. But I have x log 5 minus x log 2 equals the log 5 that was left over here. So I've got variables numbers all grouped together. And the benefit here is I can actually write this as a single variable now if I GCF out the x. Ooh, man, I'm running out of space. So that's x times log of 5 minus log of 2 equals log of 5. So what is log 5 minus log 2? It's just some number, right? So if this said 3x equals some number, what would you do to solve both sides? How would you get rid of the 3 in front of the x? If this was just like 3x equals 5, what would you do to solve for x? Divide by the 3, right? So the same idea. I'm just going to divide by this big ugly thing because it's just a number. That's all it is. So divide both sides by the log 5 minus log 2. And the thing I would want to point out is that this would be super illegal to cross those out. Super illegal. Can't do that. That's not how fractions work. So my answer is whatever this is, and I'd have to plug this into the calculator with lots and lots of parentheses, but you end up getting x equals 1.756 as our answer here. So just a way to deal with logarithms that I can solve exponential equations using them, and why not work in log base 10 because I don't have to write 10s all over the place. I would have had to write 10, probably a dozen times there or so, which would not have been fun or appreciated. So thanks for watching, friends. Have a great day. Bye-bye.